In this task, we're given a length versus time simulation. The slider on the bottom controls the time, and the domain can be changed here. And the f of x function up here actually controls the length of a black line segment. So for instance, if we did 50, it actually controls the length of this black line segment here. Okay. This blue line segment is called the target segment, and that's the one that we need to try to find the function for, potentially, and then try to get this black line segment to match the length of the blue. So in this task, you're asked to do a few things. One is determine whether or not this segment is changing according to a quadratic function or not. So that's your first charge. And first of all, the way you're going to do that is you're just going to look and see. There's a play button over here to the left that you can't see. It's a little off the screen. I'm going to hit it. First thing you're looking for is, does it have a turning point? And does it have exactly one? In this case, you see that it had a turning point there. And as far as we can tell, it does indeed have one turning point. It might have more later on. We're not looking at the entire range, but at least we don't have anything to rule it out. So far, it's a good possibility for a quadratic function. Next, we want to see are the second differences of the change in length over time linear, or are they constant? So we're going to need to collect some data here. So this is where we're going to want to go to discrete. I'm going to put in x is equal to 0, and I'm going to start making a table here. So I'll make a table, x and f of x, and we're going to collect a little bit of data here. X is 0. When x is 0, the output's 5. When x is 1, the output is 9. 2 is 15. 3, 23, and 4, 33. So now we've collected 5 pairs, and now let's examine the consecutive differences here. So in this first, we have a change of +4. In the second one, we have a change of +6, and then a change of +8, and then a change of +10. And we can see it already. If we take the second differences now, we've got +2, +2, and +2. And we see that the second differences are indeed constant. And that's a perfectly good indicator that this is indeed a quadratic function. So we're going to conclude yes on that. And since it is either a quadratic or a linear, quadratic in fact, we need to find the function. And in this case, we're just going to use a regression software. We need to input our data. So data 1 equals get our data in there. And now we're going to use the find fit function on our data set. We are going to use a times x squared plus b times x plus c, and we're going to tell it that the parameters are a, b, and c, and x is our main variable, and it's giving us an a value of 1, a b value of 3, and a c value of 5, which makes our function f of x is equal to 1x squared, or just x squared, plus 3x plus 5. And now we're going to go back and test that and make sure it actually works. So let's try it. X squared plus 3x plus 5. Bam, at least it works for this value. Let's snap that in. Looks perfect. Let's press play. Let me take it off discrete there. Yes, we got it. So that's that. That's the method. Determine if it's quadratic or not by just looking at how it behaves and then verifying with the second differences approach. If it is quadratic, you need to write the function using regression techniques with Wolfram. Have fun.